I've been tutoring Calculus 1 for over 25 years, and I can help you master your Calculus 1 final exam. That's today on High Peak Education. So, my name is Paul. Happy to help you with your Calculus 1 problems. We're going to have 20 Calculus 1 problems. We're going to walk through them step by step, showing graphs at times, showing the steps, really showing you lots of different methods, explaining it at every step. So, let's get into today's video. Okay, so here's question 1. It says find a and b so the function f of x defined below is continuous for all values of x. Okay, so we've got f of x is equal to, and it's a piecewise defined function. In other words, it's split into 3 parts. So we have x squared for x less than 1. We have ax plus b for x between 1 and 2, inclusive of the endpoints, because we have a less than or equal to 1, less than or equal to x with the 2. And then x squared plus 1 over x minus 1 for x greater than 2. Okay, so we want the values of a and b. Now, x squared is a parabola. In fact, it's the parabola that has its vertex at the origin, 0, 0. It's the parent function for the quadratic. Hopefully many of you know what that's shaped like. Ax plus b is a linear function. It should look like a line. The slope should be a, and the y-intercept should be b. And if we want this function to be continuous for all values of x, where the parabola ends at x equals 1 with an open circle, should be exactly the same y value, that's the same function value, where the linear function picks up at x equaling 1. So we need to match those up. And then we need to do the same thing with this rational function. Now, by the way, this rational function for x greater than 2, you may be saying, oh, what about its denominator being 0? Yes, if its denominator is 0, which is x equal to 1, would give it an undefined value. But an undefined or infinite value is only going to be true if you have x equal to 1, but that's not even on the domain of this part of the function. So I think that we're good. So what that means is we can just also match up the y value here with the right-hand endpoint. That is when x equals 2 for this linear function. Now, because we're looking for 2 parameters, a and b, I think we need 2 equations. The one for the left-hand endpoint and the one for the right-hand endpoint, namely x equals 1 and x equals 2. So let's go ahead and do that. Okay, so first starting with these 2, let's go ahead and get this at x equal to 1. So at x equal to 1, we should match the function values. So let's go 1 squared should equal to a times 1 plus b. So 1 squared we know to be 1, and then a times 1 is just a plus b. So let's just write that as a plus b is equal to 1. And that's our first equation. So let's label that as equation 1. Let us now proceed to the second equation, which has to do with the other 2 at x equal to 2. So for these other 2 pieces at x equal to 2, let's plug in 2 to the linear function. So we have a times 2 plus b, and we want that to equal to 2 squared plus 1 over 2 minus 1. Okay, so a times 2 is 2a, so that's 2a plus b. And then let's calculate what's going on with this rational function. 2 squared is 4, plus 1 is 5. So that's going to be 5 over 2 minus 1 is 1. By the way, we're doing it this way because exponents come before addition, and then 2 minus 1 is the only operation that's going on in the denominator, but these are implied parentheses for numerator and denominator. We do the whole numerator separate than the denominator before we do the calculation. Okay, so 5 divided by 1 is just 5. So that's 2a plus b equals 5. Okay, so let's let this be equation 2. So we have 2 equations, 2 unknowns. So I think what would be best is, because equation 1 has a single b in it, as does equation 2, let's subtract the first equation from the second equation. In other words, linear combination, sometimes called the elimination method is going to give us how we can solve for b. Okay, so notice I'm subtracting equation 1, and we're going to get the b's to go away. So switching to black to finish up the algebra, 2a minus a is just a. B minus b is just nothing. 5 minus 1 is 4, so that means a equals 4. That's good. Now we can plug that into any of the equations. I'm going to suggest we should plug back into equation 1. So we'll go 4 plus b equals 1, subtract 4 from both sides to get b, and that's b equals negative 3. So a equals 4, b equals negative 3, and we look at the choices. I think that's this third choice down. So that's exactly what we should do. Now, by the way, you can graph this. You can show where the parabola meets the linear function on the left-hand endpoint, x equals 1, and then where the linear function meets the right-hand endpoint at x equals 2, and that should work out just fine. So let's consider this problem done, and let's move on. Okay, so for this problem, we have y squared equals x to the third minus 3xy plus 3, and we want to find dy dx. Okay, so in this case, this is more of a relation than it is a function. A function would be y equals something in terms of x. In other words, the dependent variable would be in terms of the independent variable. So y is like f of x. But here you see that y is mixed in. So I think we're going to need to find dy dx by using implicit differentiation. In other words, let's take d by dx of this entire equation, that is the derivative with respect to x of this whole equation, and we'll solve for dy dx. So taking d by dx, the derivative operator, we get 2y dy dx equal to, now what's the derivative of x cubed? Well, that's going to be 3x squared. What's the derivative of 3xy with respect to x? So we have to use the product rule. So the derivative of the first term, namely the negative 3x, is minus 3, then the y remains. Then we do the derivative of the second term, namely the y, so we have minus 3x dy dx. Finally, what's the derivative of positive 3? Well, it's a constant, so it should be 0. In other words, the derivative of anything that is constant and unchanging, there's no change, so it's just 0. Okay, so we got to solve this for dy dx. So to solve, we're going to take these two terms, put them on the same side, and we're going to take these other two terms and put them on the opposite side. That is, we're going to collect, then factor, and then solve. In other words, we're going to collect the dy dx terms to one side of the equation. Then we're going to, step 2, factor out the dy dx from both the terms. Then step 3, we're going to solve by division. So moving the dy dx terms over, I think let's do plus this to this side. That's 2y dy dx plus 3x dy dx. Just moving this dy dx term over with a plus is going to give us just this right-hand side, 3x squared minus 3y. Okay, so that was step 1 completed. We collected the dy dx terms. Now let's do step 2, the most important step. In other words, factoring. Let's factor out the dy dx. Remember, this is derivative of y with respect to x, which is ultimately what we're looking for. So we have 2y plus 3x still remaining, and then the right-hand side stays exactly the same, 3x squared minus 3y. Then we just got to divide to get step 3 done, to get dy dx by itself. So that's dy dx equals 3x squared minus 3y over 2y plus 3x. Okay, so let's see which of these choices this looks most similar to. Looks like the last choice to me. So this last choice is exactly what we have. Now, by the way, sometimes people put x before y because it's alphabetical. This denominator chose not to, just like we didn't have it alphabetical. We could have switched the order and just had 3x plus 2y, but you can probably tell that this person, whoever solved this problem before us, kept it in the same order. They did it the exact same way we did. Okay, so we're going to consider that complete, and let's go ahead and move on. Okay, so for question number 3, we're asked to find the following limit. So 3 says, the limit as h approaches 0 of sine of 7 pi over 6 plus h minus sine of 7 pi over 6 all over h. Well, hopefully many of you recognize this formula. This is exactly the definition of a derivative. So if you recall, the definition of a derivative is f prime x. Prime means the derivative. And it's going to be f of x plus h minus f of x over h. But in this case, f of x is going to be the sine of x, and we're just letting x equal 7 pi over 6. Okay, so hopefully you see that here. I use kind of this pink color and this purple color. So the sine is the function, and then the x is 7 pi over 6. I hope you see that. So it exactly fits this definition. So what we really want is the derivative of sine x, because that's what this is, the derivative, but then with 7 pi over 6 plugged in. So what is the derivative of sine x? Well, that's exactly going to be cosine x. Hopefully you know that. That's a standard, well-known derivative from your tables and from your derivative sheet. And then let us plug in 7 pi over 6. Now hopefully you remember this from a unit circle. So 7 pi over 6 I think is down in quadrant 3. It's got a reference angle of pi over 6, which is like 30 degrees. And if you recall, in quadrant 3, both sine and cosine are negative, only tangent's positive. So it's the cosine of 7 pi over 6, which again would be the negative of the cosine of pi over 6, namely its reference angle. Okay? So that being said, what's the cosine of pi over 6? Well, cosine of 30 degrees, cosine of pi over 6, is square root of 3 over 2. So it's going to be negative square root of 3 over 2 for the exact answer. So that's going to be the third one down. So I believe that's the exact value of this limit. So hope that makes sense. And let's consider this complete and move on. Okay, so we have this function y equals arcsine x minus the square root of 1 minus x squared. We're looking for dy dx. So we want the derivative of this function. So the derivative of an arcsine is something that comes off of a derivative table. In other words, you can look up the formula. By the way, arcsine is the same thing as sine minus 1 notation. It means the same thing as inverse sine. We're going to do the derivative of that, and that's going to be 1 over 1 minus x squared. So let's put that in first. So that's 1 over the square root of 1 minus x squared. But then we need the derivative of this term. But this term is just like a square root. In other words, it's raised to the 1/2 power. So we have to use the chain rule on this. So for its derivative, it's minus 1/2, and then it's 1 minus x squared to the negative 1/2 power, and then you do the derivative of the inside, which is 2x with a minus, because it's minus 2x, because the derivative of negative x squared is minus 2x. Okay, so let's clean this second term up. So in terms of the second term, we should also write it with a denominator of a square root, because I think we're going to combine these with a common denominator. So this is 1 over the square root of 1 minus x squared, and then let's go minus. Now do you see that this 2 and this 1/2 should cancel? And then a minus and a minus makes a plus when we multiply them, and then there's an x in the numerator. So I think it's going to be x over the square root of 1 minus x squared. Now y over the square root of 1 minus x squared. This is a negative power, so it drops it to the bottom, and the 1/2 power is same thing as a square root. But look, we can just combine these. This is just a common denominator of the square root of 1 minus x squared, so this is 1 plus x. Okay, so this is exactly the second choice. So that is the derivative of this function. So we're going to use that second choice for the answer and move on. Okay, so for number 5, we have a u-substitution problem, but it's kind of a difficult example of a u-substitution. Okay, so this says, by an appropriate substitution, the indefinite integral of x cubed cube root of 4 minus x squared dx can be transformed into which of the following integrals? So this is going to take some fiddling around with, because I think we either need to set u equal to x cubed and then manipulate it to get the 4 minus x squared, or we want to set u equal to 4 minus x squared manipulated to get x cubed. So I think that the best choice is going to be u being 4 minus x squared. Now why? Not only will we get like a single term u under the cube root, in other words, that's raised to the 1/3 power, but then I think we will be able to solve for x cubed and manipulate from there. So let's explore this. So let's say let u equal 4 minus x squared. Okay? So then du from that would be what? Minus 2x dx. Now notice that covers a couple things from under the integral, but not quite the whole thing. So notice we still need an additional x squared, and we need to get rid of this the negative 2 by dividing by 2. In other words, we're going to get a negative 1/2 out front. So let's do that first. So we get negative 1/2 du is equal to x dx. Now notice which pieces we can cover. U is this, 4 minus x squared, so that's covered. X dx is covered by negative 1/2 du, so that's this part, and then just x to the power 1 is covered by this part, the negative 1/2 du. So we need to generate x squared. So x squared has to come from here because x to the first times x squared is going to finally cover that full x to the third. So how can we get x squared out of this? Well, notice if I add x squared over, we have u plus x squared is equal to 4. Then subtracting u, x squared is equal to 4 minus u. So let's plug all these pieces in. So the integral becomes this. The u is 4 minus x squared, and that's raised to the 1/3 power. So this is u to the 1/3 power. Notice u was 4 minus x squared. 1/3 is the same thing, power is the same thing as the cube root. Let's do negative 1/2 du. So this is negative 1/2 and du. Notice I'm putting the constant on the outside because that's exactly what covers the x dx. But then x squared is given by, so 4 minus u is going to cover this x squared. So let's put that in, 4 minus u. So we need to multiply all these things together. Now, as you can see, the answer choices looks like they're multiplied out. So let's indeed multiply this out, but let's leave the negative 1/2 on the outside. So by the way, I'm already leaning towards the third choice, but let's see if we can confirm that. So that's going to be negative 1/2 integral. It looks like the third choice has a negative 1/2, but only has a single term. So actually, maybe I'm leaning towards the first choice, but let's see how it works out. So let's multiply u to the 1/3 into each of these terms. So we get 4u to the 1/3 minus u to the 4/3. Notice I'm adding powers here because this was u to the first. And then parentheses du. Well, notice we have a subtraction, but we also have a negative on the outside. So we can bring the negative in, and then the positive term becomes negative, and then the negative term becomes positive. So I believe we will have 1/2, and then integral, and then it'll be u to the 4/3 minus 4u to the 1/3, and then parentheses, and then du. Now, is that one of the choices? Yes, indeed. It actually is the first choice. So this is a pretty challenging u-substitution as far as I can tell. So those of you doing u-substitutions in your calculus class, hopefully this helps. Let's consider this complete and correct, and we'll move on. So here we have an example of left-hand and right-hand limits of f of x as x approaches a. We have a true-false question. So if the left and right-hand limits of f of x as x approaches a exist and are equal, then f of x is continuous at x equals a. That's going to be false, because hopefully you know there's a big difference between limit existing and continuity. Continuity means the function value needs to be true there. Limit existing means the limit meets up the same value both sides. So this is going to be false. Let's consider this correct, and then we'll move on. So here we have a problem, number 7. The function 2x cubed minus 9x squared minus 24x plus 1 is increasing on. Now this is definitely a classic Calculus 1 problem where we want to understand how the function is increasing. That is, the y values are getting larger on the graph. So we think about that we could graph this and just sort of look for the intervals where the function is getting larger. But that's a little bit of like cheating to some extent, because we'd be assuming certain intervals. We're not sure if it be inclusive, exclusive, certain intervals, and so on. So the calculus, one way to do this is to calculate the first derivative and make sure it's positive. In other words, the slope of the tangent line being positive will be where the function's increasing. So we should use the power rule for derivatives. So if this function is called f of x, then the first derivative would be f prime x. So we'll do 3 times 2, that's 6, and then x squared. And then minus 9 times 2, that's minus 18x, and then minus 24. And we're going to go greater than 0, because greater than 0 is positive. Now, let's consider what's the greatest common factor of all these terms, because we just care when it's all positive, not necessarily if there's a factor that's common to all of them. So hopefully you note that 6 is the common factor to all these terms because they're all divisible by 6. So then we have x squared minus 3x minus 4, and then greater than 0. Well, we can divide both sides by 6 safely, so to say, because we know that 0 divided by 6 is just still 0. And we really care about this x squared minus 3x minus 4 being greater than 0. So now we could graph this. Now this would be a graph of a parabola for the derivative function. We could look to see where the x-intercepts are, and then take a look where the parabola is above the x-axis. That'll work as well. And I think for practice, what we should do is we should just go ahead and try to factor this. So that gives us x in the front position. In other words, we have two binomials, the product of them. X times x is x squared. And then we need two factors of negative 4 that add up to negative 3. So I believe that would be negative 4 and positive 1. So hopefully you realize if you FOILed this out, multiplied it out, you'd get exactly this quadratic. So that's going to be x equal to 4 and then x equal to negative 1. Now if you think about it, when something's greater than 0 with an inequality, we're not really solving. We actually want to consider intervals. So we're going to do a sign chart. This is sometimes called the first derivative test. So a sign chart compares x to f prime x. As part of your sign chart, I recommend putting the numbers in numerical order. So I'll put x equal to negative 1 here. And I know that at x equals negative 1, this is exactly equal to 0. So the derivative is 0 there. Extending this line out a little further, let's do x equal to 1. I know the derivative is also still 0 there. Now, let's consider, if we're looking for the sign of the derivative, what we just need to do is we need some test point. So we need something to the left of x equals negative 1. So let's test point 1 is, let's say, x equals negative 2. Test point 2 is x equal to, let's say, 0. And by the way, some of you who are watching, hopefully you squawked at me. I should have had x equal 4. By the way, these test points could be anything as long as x equals negative 2 is to the left, that is smaller than x equals negative 1. And as long as x equals 0 is between negative 1 and 4, then again, also it's fine. So you could choose any value between negative 1 and 4, not including the endpoints. So we could have chosen another simple value like x equals 1, but x equals 0 is always easy to plug in. And then finally, for our last test point, let's choose x equal to 5. All I care about is the signs of this product. So if I plug in x equals negative 2, notice negative 2 minus 4, that's a negative. And then I plug in negative 2 plus 1, that's a negative. Negative times negative is positive. I don't even care what the number is. But the point is, positive means the function is increasing because it's a positive first derivative. For test point 2, if I plug in 0, I'm going to have negative 4, which is a negative, times 1, which is a positive. Then that's a negative, so that means the function's decreasing because it's a negative first derivative. And then last but not least, if I plug in 5, I'm going to have a positive and then here a positive. So positive times positive is clearly positive, which means increasing. Now notice we get what looks to be 2 intervals from these 3 intervals for which it's increasing. It looks like everywhere from negative infinity up to negative 1, not including the negative 1 endpoint, would be increasing. And everywhere from 4 up to infinity would also be increasing. So we're going to select the intervals negative infinity to negative 1 and 4 to infinity. Okay, so that's going to be this choice here. We're going to consider this problem complete. Okay, so this is a classic Calculus 1 problem from early in the semester. In other words, it's a limits problem. We learn how to calculate limits because we want to understand how to do a limit by definition, which is the definition of a derivative. But furthermore, we also want to understand limits in terms of how we approach things and understand the concept of infinity. But in this case, notice we're going to get what's called indeterminate form. Notice if you plugged in 0, you'd end up with 0 in the denominator, but then it'd be 9 minus 0, which is 9. Square root of 9 is 3. 3 minus 3 in the numerator is 0. So 0 over 0 form, indeterminate form, means it can always be simplified. In other words, we should be able to take this fraction and somehow simplify it or change it so that we can get it to no longer be 0 over 0 form. We can find what its limit is. Now, 0 over 0 form means you don't know if it's 0, infinity, or if it's a number. We're going to find out. So notice the numerator has a square root in it. That means, given it has a minus as well, being a binomial, we should use a conjugate. In fact, the radical conjugate. Because the square root of 9 minus x plus 3, if we multiply by that for the numerator, the square root should go away. In other words, we use the difference of squares pattern. So let's do that. Let's multiply the top and the bottom by 9 minus x plus 3. And notice the 9 minus x is actually under a square root. But what we do to the numerator, we must do to the denominator to retain equality. Because whatever we multiply the top and the bottom by has to be the same value, because that's just another version of 1. We're changing the form, we're not changing the value. So 9 minus x under the square root times 9 minus x under the square root, that'll just be 9 minus x. But then, following the difference of squares pattern, negative 3 times positive 3 is minus 9, because that's 3 squared is 9. And the denominator will just be literally x times this binomial, the square root of 9 minus x, and then plus 3. Okay, but take a look. We're going to get some simplification. These 9's cancel. So 9 minus 9 is gone. And then we also have negative x over the same denominator. But now check it out. X is now a common factor of the numerator and denominator. So we'll cancel that. So then what do we get? Negative 1 over the square root of 9 minus x and then plus 3. Well, notice now we should be able to plug in x equal to 0. Because whenever you cancel things from top and bottom, generally that means you've removed the 0 over 0 issue. In other words, it's no longer in indeterminate form. So if we plug in 0 for the x value that this limit approaches, we're going to have negative 1 over the square root of 9 plus 3. Well, square root of 9 is 3, so that's going to be 3 plus 3 for the denominator. The numerator is still negative 1. That's going to be negative 1 over 6, or negative 1/6. And that is this choice here. So notice we were able to take something in indeterminate form, figure out what the limit value was by using reduction by multiplying by the conjugate. Remember, this was the conjugate, sometimes called the radical conjugate, because it has a radical with it as part of the binomial. Okay, hope that makes sense. Let's look at this question. Which one of the following curves is the graph of the function f of x equals x cubed over x squared minus 4? Okay, so this is a rational function, and we note that x squared minus 4 has two possible values for its denominator to be 0. In other words, if I factored the denominator, x squared minus 4 exactly factors to x minus 2 and x plus 2. Well, x minus 2 and x plus 2 are going to give me x equals 2 or x equals negative 2 for zeros in the denominator. Now notice these zeros in the denominator are going to manifest themselves, if they don't cancel with the numerator, they're going to manifest themselves as vertical asymptotes. So vertical asymptotes will reveal themselves in the graph. Okay? Then the question is there a horizontal asymptote? And the horizontal asymptote would be 0, that is y equals 0, if we had the order of the denominator larger than the order of the numerator. In other words, as x gets really large, we would just approach 0 on both sides. If the order of the numerator and the denominator were the same, we would take the ratio of the top and bottom leading coefficients. In this case, the numerator has a power that's 1 larger than the denominator. So believe it or not, I think that we are going to get a slant asymptote, not a horizontal asymptote, that only occurs when the numerator is 1 power higher than the denominator. Exactly 1 power higher. Okay, so how do we deal with this? So to understand the slant asymptote, what we're going to do is we're going to perform long division on this x cubed. So if we take x cubed and we divide x squared minus 4 into it, what will we get? There's really a plus 0x squared plus 0x plus 0 because we don't have any of these terms. So how many times does x squared go into x cubed? Well, x times. So x times x squared is x cubed. X times negative 4 is minus 4x. Notice I'm lining up the terms with the same order terms. I'll subtract. Then we're going to have 0 here. Then notice we've got 0x squared and then minus a negative. So minus a negative 4x is actually plus 4x. And then we bring down the 0. So how many times does x squared minus 4 go into 4x? That's actually the remainder. So the remainder is going to be x over x squared minus 4. Now, what that means is, because x divided out evenly, that's the slant asymptote. In other words, that's what this thing should look like as it approaches infinity. So it's not going to be choice B. Choice B is a horizontal asymptote. We definitely need a slant asymptote. And then we also need vertical asymptotes. Okay? Now remember, there's only 2 vertical asymptotes. So let's start looking at some other choices. Choice C, I don't think choice C is going to be correct because that has 3 vertical asymptotes. Here, and then there, and then here. Notice it looks like D, E, and A all have possibilities for slant asymptotes, but we need to understand, how does this middle portion of the graph look? Well, in order to understand that, what we probably want to do is also some x and y intercepts. So in order to do x and y intercepts, y-intercept, we let x equal to 0. So if we plug in 0, that's going to be f of 0. So that's going to be the y-intercept. So that's going to be 0 cubed over 0 minus 4. 0 squared, technically. Well, that's just going to be 0. So 0, 0 is going to be an important point. So it definitely goes through the origin. So that's this point on any of these graphs. Now, it's worth plugging in, let's say x equals 1 and x equals negative 1. Why? Well, because we want to determine, is this function increasing, decreasing, whatnot. Now, we could do derivatives. We could do calculus 1 for that, but I would also say just plugging in is going to be probably just fine. So let us do f of 1. So if I put in 1, I'm going to have 1 cubed, that's 1, over 1 squared minus 4. So that's 1 over negative 3, so negative a third. So negative a third. If I plug in negative 1, so that's going to be f of negative 1, that's going to equal to negative 1 cubed is negative 1 over negative 1 squared is 1 minus 4. That's going to be 1/3. So think about this. 1/3 is positive, negative 1/3 is negative, but then when x is equal to negative 1, we're on the positive side. So that to me seems like it's right here or maybe right here. And then when x equals 1, that's going to be either right here or right here. Okay? So we're really down between E and A. D would be incorrect. Now between E and A, we have to just understand how these rational functions look. So it turns out A is a lot more like a rational function because notice it doesn't just sort of snake through and it just kind of gently goes like this. It turns out that rational functions will have an asymptote. And then furthermore, one of the things we could do is we could also plug in some values down here versus here and see which is different. So suppose I plugged in negative 5. Notice negative 5 is either going to be above y equals negative 5 or it's going to be down here below negative 5. So if I plugged in negative 5, for example, what's f of negative 5? Well, negative 5 cubed, I think, is negative 125. For the denominator, negative 5 squared is 25 minus 4, so that's 21. So negative 125 divided by 21 is going to be negative 5.95. So negative 5.95 is less than negative 5. So that would be right here. So indeed, we do have the correct answer, choice A. This was a little tricky because understanding rational functions is not easy for everybody. Okay, so now we have the correct answer. Let's move on. So this question is a classic limits question which requires understanding of calculus to calculate. Notice if we put in 0, we'd end up with 1 and then 1 raised to the cotangent of 0. Now I don't necessarily know the cotangent of 0 off the top of my head, but I know what the tangent of 0 is. That's 0. And when we flip it, that is when we take the reciprocal of tangent, so 1 over tangent of 0, so it's 1 over 0, it's infinity. So this is like 1 raised to the infinity. So we're not 100% sure what this should be. Now, intuitively, it sounds like it maybe should be 1. But whenever we've got infinities in the problem, we need to kind of deal with this. Notice, whenever we have x raised to a power of x, that's basically like a stack of functions in terms of exponents. So what we should do is we should set this equal to y, or maybe you could even call it L, which would be some limit value. And then what we should do is we should think about how to bring this power which deals with x down. So generally the method to do this is to take a natural log. So if I take the natural log of both sides, I'm going to have the ln of 1 plus 2x raised to the cotangent of x equal to the natural log of L, L being the limit. So the cotangent of x from the properties of natural logs can come down front. So we have cotangent of x times the natural log of 1 plus 2x. So now, if I plugged in 0, what would I get? So the cotangent of 0 is still infinity. Oh, sorry, the ln of 1 is 0. So I'm not sure. Is that infinity? Is that 0? What? So what we should do is we should produce indeterminate form, either 0 over 0 or infinity over infinity. Now, this is a little bit of a trick, but it turns out since cotangent is a reciprocal function, we can make it into a tangent if we put it down below. In other words, if we take cotangent of x and make it into tangent of x in the bottom of a denominator, that's the reciprocal, and that'll be exactly equivalent. So if we have ln of 1 plus 2x over the tangent of x, then we have something that we could work with, because now this is just 0 over 0 form. It's indeterminate form, equals to the natural log of this limit. And then now this is a good candidate for L'Hopital's rule. Okay? I'm not sure if I'm spelling it right. I do have a video on this channel about L'Hopital's rule, but it turns out that when we have a limit, you could take the derivative of the numerator over the denominator and it gives you the same limit value as long as it's in indeterminate form. So the derivative of the numerator is going to be the derivative of a natural log, which is going to be the derivative of what's in parentheses, 2 over 1 plus 2x. And this is over. Now what's the derivative of tangent? So I think that's secant squared. So secant squared x. Okay, now this is a fraction which we need to work with. So 2 over 1 plus 2x times secant squared, divided by secant squared x is the same thing as timesing by 1 over secant squared x. So this is 2 over 1 plus 2x times 1 over secant squared x. But wait a minute, 1 over secant squared x, that's just cosine squared x. So this is exactly 2 cosine squared x over 1 plus 2x. Now that is much easier to plug into, namely 0. So if I put in 0, the cosine of 0 is 1. Cosine of 0 being 1 squared is just 1 times 2. So I get the numerator is 2. The denominator I'm plugging in 0, so that term becomes 0. Then you just get 1. So 2 over 1, that's just 2. Now 2 is not the correct answer yet. Why? Because 2 is equal to the natural log of the limit. Remember, we took the natural log at the beginning. So now we need to exponentiate both sides. So if we exponentiate both sides, they both become e to the second, e to the ln of L. So that's e squared is equal to L. So this limit, believe it or not, is e squared. E being the natural base. So that is our answer. E squared is this limit value. So this is kind of a tough one where we had to understand taking the natural log, understand how to get this in indeterminate form, use L'Hopital's rule, plug in, and then exponentiate both sides, and then finally get our limit. Hope that makes sense. Hey, we're now halfway through this sample exam, so if you're enjoying this video, please visit highpeakeducation.com. Feel free to contact us, work with us. I can help you in all kinds of things, and we have a growing and thriving business ready to help you with all of your math, science, physics, computer science, meteorology, atmospheric science, all kinds of things that we can help you with. And we have lots of tutors that we're partnering with as well. So we're a full education solution. So please check us out, highpeakeducation.com. Let's get back to today's video. Okay, so for number 11 here, we're going to find the derivative of this function. Capital F of x is equal to the integral from pi to sine x of secant t dt. Hopefully many of you are aware of this. If we want the derivative, then we're going to take d by dx of this equation. Notice the t is going to integrate away because that's sort of a dummy variable. When I mean by dummy, I don't mean stupid. I mean like a crash dummy. Like a crash dummy in those simulations is something that stands in. So this t stands in and integrates away. Notice this is the same thing as the second fundamental theorem of calculus, where a derivative and an integral cancel each other out, but they cancel each other out where we have to put in the limits. So to put in the limits, we're going to have capital F prime x equals to, and notice the derivative and the integral go away, but we still need to use the fundamental theorem of calculus, upper minus lower. So we're going to put in for t sine x. So we've got secant of sine x, and then for dt right here, what we need is we need the derivative of this upper bound. So that's cosine x. Then what do we have? We have minus, because the fundamental theorem of calculus says upper minus lower, then it's going to be the secant of pi But then what's the derivative of any constant? Well, it's going to be 0. So this term is gone. So then what do we have? We just have capital F prime x is equal to the secant of the sine of x times cosine x. Okay, so believe it or not, that's pretty complicated looking, but that is exactly our answer. So this problem would be very difficult to integrate, or at least somewhat difficult to integrate. You could then put in the bounds, you'd have to calculate. That'd be a lot harder to do. Then you could take the derivative later, but it's much easier to just take a derivative from the beginning, get rid of the integral, and then use the second fundamental theorem of calculus. Hope that makes sense. Okay, so for this problem, what we have is we have a function that's e to the x plus 1 power times the hyperbolic cosine of x, and we want to find f prime of 0. So in other words, this function f is the product of an exponential and a hyperbolic cosine function. Now, not every one of you have done hyperbolic functions, so I'm showing you two basic derivatives. So here's the derivative of hyperbolic sine, here's the derivative of hyperbolic cosine. Turns out that they're co-derivatives of each other. And then here's the definition of hyperbolic sine and hyperbolic cosine in terms of these exponentials. Well, what we should do is we should use the product rule on this function, and then when we get to the hyperbolic cosine derivative, it's hyperbolic sine. And then we'll use this definition to plug in. Okay, so let's get this started. That's f prime of x equal to, and again, it's the product rule. So the derivative of the first term is going to be the derivative of the exponent, which is just 1, and then 1, and then e to the x plus 1, and then the hyperbolic cosine stays. So hyperbolic cosine of x. Then we'll do plus, because it's the product rule. Then we leave the first term alone. The first term is e to the x plus 1, but then the derivative of hyperbolic cosine is hyperbolic sine. So this is e to the x plus 1, hyperbolic sine. Now that we have this, let's go ahead and plug in 0. So we've got f prime of 0 equals to, that's going to be e, and then when we plug in 0 for x, we're just going to have e to the first, hyperbolic cosine of 0 plus e to the first, and then it's going to be hyperbolic sine of 0. Now let's see what happens when we plug in 0 to, first of all, hyperbolic cosine. So that's e plus e to the 0 plus e to the 0. That's just going to be a half. So that's going to be e times a half. Then let's go plus. This is e to the first, and then put in 0. This is 1 minus 1. So that's just going to be 0 for the hyperbolic sine term. So we're just going to get e. Oh, sorry, I said a half, but I should have said e to the 0 is 1. E to the negative 0, which is like e to the 0 is 1. So that's 2 over 2. And then 2 over 2 here is actually just going to be 1. So this should be 2 over 2. So 2 over 2 is 1. 1 times e is e. So e should be this function value at x equal to 0. So this is exactly e, the natural exponential base, approximately 2.718, rounded to 3 decimal places. Okay, so this may not be a problem that some of you have seen before, but hopefully it helps. Hope that makes sense. Okay, so this is a classic trig problem where we need to kind of work out a trig with an inverse trig. So what do we mean by this? Cosine of arctangent of x. So give us the cosine of an angle whose arctangent is x. So I suggest draw a picture, namely a right triangle. So if we draw a right triangle, imagine that this right here is the angle. Why the angle theta? Well, because cosine has to be taken of an angle, and imagine this is the angle theta. But that angle theta has an arctan of x. Now remember, arctangent means opposite over adjacent. In other words, the ratio of the sides of this angle theta should be x to 1. Now, we can finish out this right triangle. I can put the right angle down here in the corner. To get the hypotenuse, we use the Pythagorean theorem. So that's going to be 1 squared plus x squared and square rooted. So that's going to be 1 squared plus x squared square rooted is exactly this hypotenuse. Now we want the cosine of this triangle. In other words, the cosine of this angle theta. Well, cosine is adjacent over hypotenuse. So adjacent over hypotenuse is going to be 1 over the square root of 1 plus x squared. Okay, so that's going to be exactly this first term. Okay, so make sure you understand when we did this. Arctangent is the same thing as inverse tangent of x. Remember, inverse tangent, the output is an angle. The input's a ratio. So x is the same thing as x over 1. So that's exactly what we see here for opposite over adjacent. But then we can solve for the hypotenuse just using the Pythagorean theorem by leg 1 squared plus leg 2 squared equals hypotenuse squared. Take the square root, we get this. But then, remember, the output of that inverse tangent of x represents an angle. And the cosine of that angle is exactly adjacent over hypotenuse, and that's 1 over the square root of 1 plus x squared, which is exactly this term. Hope that makes sense. So here we have a problem where we're given f as a differentiable function, and we have the table below, and we want to know which of the following statements is true, or if there's multiple statements that are true, we want to mention that down here in terms of let's choose the correct Roman numerals. Okay, so it looks like we have information about the function at 0, 1, and 2 for the x values. We have the function value, its derivative, and its second derivative. Remember, the function value is like the y values, the derivative is like the slope of the tangent line, and then the second derivative is like the concavity. So concave up would be positive concavity, concave down would be negative concavity. The derivative is positive when the function's increasing, the derivative is negative when the function is decreasing. And looks like we're asked about local maxes and mins, or perhaps like decreasing values. Okay, so let's look at this. F has a local maximum value at x equals 0. So if we were at x equals 0, then the first derivative would need to be 0, and the second derivative would need to be negative. Well, that's true. That's exactly what we see here. So indeed, this is exactly where the maximum value at x equals 0, because again, at a maximum point, you've got negative concavity, and the first derivative is 0 because that's a horizontal slope of the tangent line. Okay, so I would say definitely number 1 is true. How about number 2? F has a local maximum value at x equals 2. So the first derivative needs to be 0, and the second derivative, now this time it's actually, the second derivative is positive. So that'd be like the bottom of a bowl. That would be a local minimum. So I'm going to suggest that this is incorrect because that would have to be a minimum. Okay, so that would be a local minimum. So Roman numeral 2 is not correct. How about Roman numeral 3? It says f is decreasing at x equals 1. So decreasing just means that the first derivative is negative, and that's exactly what we see. So we see at x equals 1, the first derivative is negative, and so the function is decreasing at that point. So we're going to say numbers 1 and 3 in terms of the Roman numerals. 1 and 3. So that's this choice. All right, so we have the correct answer. Let's move on. So what we have here is a problem which is a polynomial, x to the fifth minus 2x plus 5 equals 0, which is not factorable, which we are looking for the roots, that is the zeros or the solutions. But in order to find that solution, what we want to do is find what the numerical approximation of this is using Newton's method. So x1 is our initial guess, x2 is our second guess. So in this case, we're going to use Newton's method, which is this formula, and we're going to let n equal 1. The reason we're going to let n equal 1 is because all the information on the right-hand side is all in terms of x1, mainly being x equal to 1, and then we're going to get information about x2. In other words, the second iteration, the second guess for the x value. Now, by the way, it might be useful to graph this function to make sure that we don't go on the wrong side of a maximum or minimum value. This is actually wrapped up in the Newton's method theory. By the way, Newton's method is sometimes called the Newton-Raphson method. So here's a snippet of the graph of x to the power 5 minus 2x plus 5. So you can see it's kind of a bit of an S-curve here. And what we're interested in is finding this x value down here. But we're going to start at x equals 1. So starting at x equals 1, what we're going to do is we're going to have a tangent line that's parallel to this. That's what the derivative has to do with. And we're going to see what Newton's method, that's the Newton-Raphson method, gives us. Now, by the way, one more thing. It's very possible we might not get closer to the correct answer, but in this case, maybe we will. But let's see. So in our case, we're going to say x2 equals x1 minus f of x1 over f prime of x1. So we are going to need the derivative. So the derivative is 5x to the fourth minus 2. And now let's plug in x1, which is equal to 1. So we get 5 times 1 to the fourth minus 2. So that's just 5 minus 2, which is 3. So we have 3 for this derivative value. What happens if we plug in x equals 1 here? Well, f of 1, that would be 1 to the fifth minus 2 times 1 plus 5. So that's 1 minus 2, which is negative 1, plus 5, and that's equal to 4. So plugging into this formula now, x1 is 1 minus f of x1 we know to be 4, and then f prime of x1 we know to be 3. So that's 1 minus 4 thirds. Now 1 minus 4 thirds, we need a common denominator. That's 3 thirds minus 4 thirds, and that gives you negative 1 third. So hopefully you see this derivative will actually hit right about here at negative 1 third. And that's going to be our x2 value. Okay? So then the goal after that is to use the Newton-Raphson method again to get as close to this x-intercept as possible. Now, we need to follow this procedure forward to see if we're actually going to approach this x-intercept, this 0. But in any case, we're at least a lot closer than we were just by using the Newton-Raphson method once. Okay, so hope that makes sense. Newton's method for approximating roots. It's a numerical way to get a 0 from a function that you can't factor. So hope that makes sense, and let's move on. Okay, so now to problem 16. What we have is we have a polynomial in the numerator, 6x to the third plus x. We have a cube root in the denominator. So we have 13 plus x to the ninth underneath a cube root. So what that means is we're going to look at this limit as x approaches 0, but we need to consider the order of the numerator and denominator. In other words, what's the highest power in the numerator and the denominator? So we note that it's x to the third in the numerator, and in the denominator it's actually x to the third. Now why is that? Because it's underneath a umbrella of a 1/3 power. That's the cube root. So effectively, we could perform this problem using L'Hopital's rule. And I think that would be a little more complicated than necessary because the derivative in the bottom would require the chain rule. So I'm going to recommend we divide through by the largest power of x, and that's going to be x to the third. So let's do that for each of these. So we get 6 plus 1 over x squared. Notice we got 1 over x squared because x over x to the third is 1 over x squared. Dividing this through by x cubed is like dividing by x to the ninth under a cube root. So this is the same thing as the cube root of x to the ninth. We divide through by the highest power. We have the cube root of 13 over x to the ninth plus 1. Now notice we're still taking the limit as x approaches infinity. So hopefully you know that this term and this term will both go to 0. Why to 0? Because when you have an infinity in the denominator and you have a numerical value in the numerator, when you approach the biggest number you could think of, you're dividing by the biggest number you could think of, and that's going to give you 0. So 1 divided by the biggest number you could think of is just going to approach 0, because it just gets very, very small. So effectively, this is going to approach 6 over, now that's 0, and then we do the cube root of 1. Cube root of 1 is just 1. So 6 over 1, that's just going to give us 6. So I believe that 6 will indeed be the correct answer here. That's going to be the limit value that we approach. Hope that makes sense, and we can move on. Let's look at number 17. For what value of k will f of x be continuous for all values of x? So we have x squared minus 3k over x minus 3, x between negative infinity and 2, inclusive of the right endpoint, and then 8x minus k for x between 2 and infinity, not including the 2. Okay, so what we need is, first of all, the fact that this function here, x squared minus 3k over x minus 3, that's a rational function. It'll actually have a vertical asymptote at x equals 3. But notice x equals 3 is not even on this domain, so we're not even going to worry about it. This function is continuous for all x values on the domain that's given, negative infinity to 2. Now, what we need is we need this y value, that's this function value, to match up with this y value. This rational function meets up with a linear function. So we're going to change the value of k. So in other words, we just literally need to set these two branches, these two pieces, equal to each other. So let's do that. That's x squared minus 3k over x minus 3 equals to 8x minus k. Now, what we probably should do is we want to eliminate fractions if possible. So let's multiply through by x minus 3. So we get x squared minus 3k equals to 8x minus k times x minus 3. Okay, now this on the right-hand side will be a quadratic, but this is also a quadratic. So I think we need to kind of multiply terms out, start either comparing them or, for that matter, solving. So let's FOIL this out. So first outer, inner, last terms. So 8x times x is 8x squared. 8x times negative 3 is minus 24x. And then minus k times x is minus kx. And then minus k times positive 3 is plus 3k. Remember, k is a constant. And then that's equal to x squared minus 3k. All right, so we should match up like terms. This is an x squared term. This is an x squared term. This is a 3k term. Here's a 3k term. And then this is x. And then this is also an x term. Okay, so let's be careful. Let's subtract x squared from both sides. Let's also add 3k to both sides. Okay, so let's see what we get. We have 0 equals 7x squared. And then how about these x terms? So it's negative 24x minus kx. They both have a negative. Let's factor that out. 24 plus k. And then they both have an x. Let's factor out the x to the right-hand side. Now notice that kind of shows us what the coefficient looks like on this x term. And then 3k plus 3k is plus 6k. All right, now we have a quadratic, which is not easily solved. And it turns out what we want to do is we want to find the k values. Now, by the way, we might find multiple k values, but we need a k value that actually fits this situation. So remember, I think that this equation is valid when exactly x equals 2. So x equals 2 is the value for which this should occur. So let's plug that in and then we'll find k. So we've got 0 equals 7 times 2 squared minus or plus k times 2 and then plus 6k. All right, so this is exactly what we're going to have for solving. So we're going to get 7 times 2 squared. So 7 times 4 is 28. We have 0 here. And then let's go minus. And then this is, let's distribute the 2 in. So we're going to have minus 2 distributed in. So that's 48 minus 2k plus 6k. Okay, so we're almost there. So negative 2k plus 6k, I think, is 4k. So that's 4k. And then equals, let's move 28 minus 48 is negative 20. But then we moved it to the other side, so it's a plus. So that's 20 equals 4k. Divide by 4, we get k equals 5. Okay, so this is the numerical way to solve for k equals 5. So I've got k equals 5 marked here. Now there's also a Desmos way to solve this. In other words, you can do this graphically. I'm about to show that in just a moment. So here we have the Desmos graph. Here I've got x squared minus 3k over x minus 3. And then we've got x, 8x minus k. Notice I specify the domain, x less than or equal to 2, and then x greater than 2. Notice the default value that Desmos gives me is k equals 1. So let's use the slider to see if we can get these to match up. And look at this. It looks like they come together right as k equals 5. Okay, so here we have a limit as x approaches infinity of arc cosine of 1 minus x over 2x plus 3. And it looks like the possible answers are in terms of pi. So we're looking for some sort of special value. Well, we've kind of done this in other problems, but I think that instead of using natural log, because that doesn't seem reasonable because we don't have something of x raised to something of x, I think that we can call this the limit L, and let's just take the cosine of both sides, because that eliminates arc cosine. So we could say 1 minus x over 2x plus 3 is equal to the cosine of this limit. And remember, we still have x approaching infinity. Well, with x approaching infinity, what we just do now is the powers that are largest, x to the power 1, x to the power 1, are matching top and bottom. In other words, the order of the numerator is linear. The order of the denominator is also linear. So we should just be able to take the ratio of the leading coefficients. So if we take the ratio of the leading coefficients, that's going to be negative 1 over 2. So that's negative 1/2 equals the cosine of L. Well, then we just need to solve that. So we need to say the arc cosine, same thing as inverse cosine, of negative 1/2 gives us this limit L. Now remember, arc cosine has a certain range for its function. I think it's defined between 0 and pi. In other words, quadrants 1 and 2. So arc cosine of negative 1/2 is going to be in quadrant 2 because all trig functions are valued as positive in quadrant 1. And negative 1/2 for the ratio, so you think about a triangle that has negative 1/2 for its cosine value, and I think that's going to be a reference angle of 60 degrees or pi over 3 radians. So if you recall, a quick sketch of something in the unit circle, we have 60 degrees here. So this is 120 degrees. But how do we get that in radians? And so hopefully you know that 120 degrees is the same thing as 2 pi over 3 radians. So let's go ahead and mark 2 pi over 3 radians right here for the correct answer. And that's because it has a reference angle of pi over 3, 60 degrees, in quadrant 2. And so 2 pi over 3 for the correct answer. All right, so let's consider that correct and then move on. Okay, so now we're asked to solve x squared minus x minus 6 greater than 0. This is actually very similar to a problem we did before when we had an inequality where we wanted to find out where a function was increasing. So we just gonna factor this. In other words, this is just like saying, where is the parabola above the x-axis? So if we factor this, what are two factors of negative 6 that add up to negative 1? Well, it's going to be negative 3 and positive 2. So that's x minus 3, x plus 2 greater than 0. And then now let's set up a little sign chart. So let's look at x versus f of x. So when x is -2, we know the function is equal to 0. When x is equal to 3, we know the function is equal to 0. So we're just going to do some test points. So we're going to test these 3 points, and all we care about is if it's positive or negative. So if we test, let's say, -3, we could test x equals 0, and we could test x equals 4. We just have to plug this into this quadratic. And it's easier to plug into the factored form than it is the standard form, because the factored form, all we care about is the signs, positive or negative. So plug in -3, then we have a negative times a negative, which is a positive. So that works in terms of this interval. If we plug in 0, we have -3 times +2. Negative times positive is negative, and so that doesn't work. And then last but not least, we'll plug in 4, and that's going to be 4 minus 3, which is 1, and then 4 plus 2, which is 6. The key is it's positive, so that interval works. So we get 2 intervals. The interval up to -2 and the interval from 3 and above. So from -infinity to -2, non-inclusive, and then from 3 to infinity, non-inclusive of the 3, we unite. That's a union symbol, which means take both those intervals, and that's going to be when this is greater than 0. By the way, if you did look at the graph, it'd be an upward-facing parabola, and to the left of the left x-intercept and to the right of the right x-intercept, that's going to be when the parabola is above the x-axis. So that's going to be exactly these 2 intervals. Okay, hope that makes sense. So here we have, find the equation of the tangent line to the curve y squared plus 4xy plus x squared equals 13 at the point 2, 1. Well, notice, again, this is a relation, because if y was like f of x, then y squared and y in there, they're kind of mixed and interrelated to each other. So what we should do is we should go ahead and take the implicit derivative of this equation. So we're going to take d by dx of this equation. So what does that give us? The derivative of y squared with respect to x would be 2y dy dx. Then we have a product of something that depends upon x and something that depends upon x. So we have to use the product rule. So plus 4, and then we still have the y, because the derivative of 4x is just 4 with respect to x. Then let's go plus the derivative of this with respect to x is 4x dy dx. Sorry, just 2x. The derivative of a constant is 0. So this entire equation is equal to 0 after we do the derivative. Well, we need to solve this for dy dx, because dy dx is the derivative. So we need to move the 4y and then the 2x over. So let's go minus 2x minus 4y is equal to, let's see, 2... Actually, let me arrange x before y as well. Let me reorder these terms. 4x dy dx plus 2y dy dx. Now notice, we have a couple of ways we can simplify here. I can factor out -2, and then we have x plus 2y. I can also factor out a 2 here. So we've got 2x dy dx plus y dy dx. Now, since all the terms are even, we can just cancel this 2. Then we need to factor out dy dx. So that's dy dx 2x plus y. And then just divide. So on the other side, we're going to get dy dx after division is equal to, and it's going to be, now we can think about, there's one negative, so we can keep the negative out front. And then we've got x plus 2y divided by 2x plus y. Okay, so that's our implicit derivative. Now we need to use the point 2, 1. So let's use the point where x is 2 and y is 1. So we plug that in, x is 2, so that's 2 plus 2 times 1, and then 2 times 2 plus 1. Okay, so that's 2 plus 2 is 4, And then this is 2 times 2, which is 4, plus 1 is 5. So negative 4/5. So negative 4/5 should be the slope. So that's m. Now notice we're already thinking about either one of these two choices, because those both have a slope of negative 4/5. So if you were on a standardized exam, I would eliminate the first 3 choices. But then we still need to get the equation of the tangent line. So we need y equals mx plus b. So this is the slope-intercept form of the equation of a line, y equals mx plus b. And we have the slope and we have the point, 2, 1. So we'll put 1 in for y. We'll put the slope in as negative 4/5. Then we'll put the x value in as 2 plus b. So then 2 times negative 4/5 is negative 8/5 plus b. We need to write 1 in terms of fifths, common denominator. So that's 5/5. So now I think we can add 8/5 to both sides. So we're going to get 13/5 is equal to b. Now that we have b, we can write the full equation of the line. So y equals m, which is the slope, negative 4/5 x plus 13/5, 13 over 5. Now let's check. Yes, indeed, that is the last choice here. So this last choice is the correct answer. So what we find here is that this curve, y squared plus 4xy plus x squared equals 13, if you had factored it and changed its form, this actually would be a hyperbola. But it'd be a hyperbola also that's not even along the x or y axes in terms of its transverse axis and conjugate axis. So you can kind of see this is a hyperbola looking thing shown there in red. I've labeled the point 2, 1 on the xy axes right here in blue. And notice that y equals negative 4/5 x plus 13 over 5 is indeed the tangent line to this curve. So we now have finished this sample exam. Congratulations for getting through all 20 problems. Hope that makes a lot of sense. And thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel to join the channel. Social media links are down in the description box below. We really appreciate your support. Please reach out to us if you have questions, comments, concerns. You want another video to be made here by us, and we will see you in the next video.